Now let us consider the motion of the wave. In this case, the wave is moving to the right with a velocity v, and this picture shows the propagation of the wave. After time t, the point at one of its crest has moved a distance v times t. Now we have to modify the expression for the displacement because we have to add in the variable time, and so this becomes the displacement becomes a function of both position and time in this case, and the argument also has to involve the variable time. So this instead of x we have to use x minus vt because the previous position has moved by a distance vt in the wave. Now the modified wave equation is shown here, and now we will do some manipulation and rename some of the variables. So the argument of the sine has this factor 2 pi over lambda. So we will multiply this throughout, and then we have instead of lambda we will substitute f, the frequency, because v equals f lambda as we have shown. So v over lambda we can substitute it with f, and then if we rename the variables 2 pi over lambda as k, and 2 pi f we know is omega, the angular frequency, we have already described it. So we have this new variable or new constant called k, and what is the k? K is given by this expression 2 pi over lambda. So this is called the wave number. This is also known as the spatial frequency. This means the number of wavelengths per unit length. This has the symbol as shown. The symbol is k, and its unit is radians per meter. So then we encountered some new terms. In this case, the phase is given by kx minus omega t. This is the angle theta basically. And then the phase velocity v equals f lambda. This can be expressed in terms of omega and k also. After some manipulation, we see that this is equals omega over k. So the phase velocity v equals omega over k. So for here we show some general expressions for traveling waves. This has the form, this can assume the forms of sinusoids or cosines as shown here. And notice the sign of the term omega t. This can be either positive or negative. Minus sign indicates a wave traveling to the right, and a plus sign indicates a wave traveling to the left. And notice the angle phi. This is the phase angle, that is the offset, phase offset in the wave. Now let us look at an example. Suppose we are given an equation for displacement in terms of position and time as shown here, dm times sine of kx minus omega t, and we are given k to be equal to 2 pi and omega to be equal to 2 pi also, and dm equals 1 in this case. So we will plot how the wave looks like as time passes. And also notice the phase offset here is 0. So this is how the wave looks at t equal to 0 seconds. It is a sinusoid. So if we set t equal to 0, we just have sine kx as shown here. Then if we set t equal to 0.25 seconds, then we see the wave has moved now. And then at 0.5 seconds, the wave has traveled by basically by a phase of 180 degrees. So this is just a plot of that equation. Graphically, it looks like this. And as time passes, the wave is propagating to the right. You can see other examples of traveling sine waves from these physics clips by Professor Joe Wolf.